We were going to do polar, non-polar molecule review, and then it struck me that, it'd probably be a good idea for us to review geometries one more time, because this will be the thing you go, I didn't understand it, it's hard. So I thought, how can we go over the review of that in a way that would be the most beneficial to you? And so I was busy this weekend. I've got my molecules all made over there. We'll take a look at all those in just a moment. Labs are tomorrow. It's in I now. It's been there for a while. So let me see if this is a good marker. It's an adequate marker. Cool. I haven't thought out this review in a lot of detail, but let's go ahead and do a review. Let's say we have a molecule, and it's kind of like reproducing the chart that you have in your chapter, but I think it'll benefit you to see it and me have the models to show you. Let's go ahead and start with the way I taught it, which is some people start with homonuclear diatomics and build up from there. I think it's more beneficial to start with the most complex one, because it has the most number of molecules that have that as an option. I mean, not the most number, but of all the different geometries, start with the one that has the most variance. And so what we're going to start with is the tetrahedral. Pretty sure that's the sequence I taught them in here. This model I made here is a model of a tetrahedral. See? Tetrahedral has a central atom. On our VSEPR, this would be like our pivot atom, the black ones, and all the external atoms are going to be shown in red. Okay, obviously the wood dowels represent a covalent bond. Okay, so a tetrahedral. So the number of connections, or the number of, I'll just call it the number of points. How's that? Now, what do I mean by the number of points? Is either the number of bonds or the number of unbonded electron pairs that are about the central atom. So in this tetrahedral, there are 4 of them. 1, 2, 3, 4. All 4 of them are bonds. Okay? So the number of points being 4, the number of bonds is also 4 in this case. You can also then say the number of unbonded pairs that's equal to 0, right? There are no unbonded pairs here. The unbonded pairs, when we pull the other models out, are represented by the 2 white electrons, or 2 white balls that'll be glued to the central atom. So there are 4 points with 4 bonds, no unbonded pairs. The shape tetrahedral, and the bond angle. So the angle between any one of these, in this model, between these wooden dowels, the angle between, the bond angle between the external atoms in the molecule, between any one of those is going to be what angle? 109 degrees, right? So 4 points, 4 bonds, no unbonded pairs. The shape is a tetrahedral and 109 degrees. So for 4 points, for all of the ones that are 4 points, it's going to be based on tetrahedral. Okay? So everything that has 4 points is going to be based on tetrahedral. Let's say that we've got 4 points and we only have 3 bonds. If we've got 4 points around the central atom but only 3 bonds, that means we have 1 unbonded pair. If we were to take this shape then and remove one of the bonds and replace it with an unbonded pair, it would look like this. So in this case, I've oriented the bond upward, is replaced in this case by the unbonded pair of electrons. Otherwise, it's the same. And whereas this was a tetrahedral, this one, the shape here is a pyramidal. The tripod the camera's on. Remember I told you, encouraged you to think of it as a tripod with a camera on the top? So this shape here is the pyramidal. And the unbonded electron pair, how does the force that it exerts different than a bond would be? An unbonded pair exerts more force repelling the other bonds, okay? Repelling the other electron pairs that are bonded. And so, since it repels stronger than a bonded pair would, it's actually squeezing these other three. It's pushing them away, kind of forcing them closer together. Since the angle here used to be 109 degrees, but it's a little bit closer now, we note that as being 107 degrees. Because this unbonded pair here is pushing the other bonds away more than a bonded pair would be. Because think of it this way. If you have a bonded pair here, sometimes those electrons are at this external atom, right? Sometimes the electrons are away from the center and exerting less force down. Here with the unbonded pair, they're staying close to center. And staying that close to center, they exert a more consistent force away on these other atoms, squeezing these legs together and creating 107 degrees. If we have 4 points of connection and only 2 bonds, that means we're going to have 2 unbonded pairs, because you're going to note that every one of these, if there's 4 points, the sum of these two has to equal 4. 4 bonds with no unbonded, 3 bonds with 1 unbonded, 2 bonds with 2 unbonded. Replace 2 of those bonds with 2 unbonded pairs. Now remember, every one of these points are still equidistant apart. If you start from a tetrahedral perspective, now these unbonded pairs are going to repel each other a little bit more, and together they're going to push these other bonded pairs even farther apart. This is a water molecule. This is a representation of a water molecule, yeah. So this would be H and H around a central oxygen. The oxygen has 2 unbonded pairs. And water is the primary example we use. The shape is bent. And the bond angle between these 2 bonds, 105 degrees. Right. So if you come over here, I'm going to replace this little note here about based on tetrahedral. Put that to the outside, because every one that has 4 points of connection around the central atom is based on a tetrahedral. Okay? So if your central atom can have 4 points of connection, it's going to be any combination of either 4 bonds, 3 bonds, or 2 bonds. Now if we get down to 1 bond, we're talking linear again, so we're leaving that one out. That would be a possibility, right? 1 bond with 3 unbonded pair, but that's the combination of just 2 atoms. We'll get to that later. Is this helpful to see it this way? Okay. And I'll probably try to leave these in class somewhere. Several people suggested that I hang them from the ceiling, but when the grade schoolers come in here, do you really think they're going to survive? I don't think so. I put way too much work in here. I would say I spent hours and hours and hours on this, but that would be a lie. I just spent a lot of time on it. All right, the next series, or the next geometry that we're going to use would be the number of points. Could go ahead and just kind of segment this whole thing off. Those are all based on tetrahedral, and we're going to do the ones now that are based on tetrahedral has 4 points of connection. The next series is going to be based upon 3 points of connection. Three points of connection around the central atom. In this case, 3 points of connection with 3 bonds and no unbonded pairs. Remember I said before that this when you represent it on the VSEPR shape, when you do your VSEPR geometries, draw the shape, that you could actually draw this shape on the board and get a good representation of it, what it looks like in 3 dimensionals, showing it in 2 dimensionals, because it doesn't have any bonds coming out towards you or any bonds going back away from you. All the bonds are in a plane. And so when you draw this VSEPR on the board, it's going to closely approximate what it really looks like, because there are no bonds coming in or out. So we have all 3 of these atoms are going to push away equally. And what is the angle going to be between these here? 120 degrees all the way around. That's right, 120 degrees. If any one of these atoms were to shift in any direction, it would immediately have a greater repulsion. Let's say that this atom, for some reason, ends up shifting over to this side. Well, it would either bound back because it's got a greater repulsion coming from this atom than it does this one, and so equalizing force would bring it back. Or, you know, if for whatever reason this stayed placed, this would shift over, and they would automatically rearrange themselves in a perfect 120-degree angle between all 3 points. It's always going to stay 120 degrees. Yet, so the first part of the name we get is, or the name that you've learned is what? What kind of shape is this? Trigonal. It's a trigonal. Sometimes you'll see it called a trigonal planar. Why is it called trigonal planar? Because the molecule itself is, you see from the front, is trigonal. If you looked at it from the side, all of the atoms are in a plane. See? It's trigonal from the front, and they all rest in one plane. There you go, camera. There. There. See? So the trigonal or trigonal planar. And the next shape we're going to have here is also based on a trigonal. If we were to take one of these bonds away, and yet we still had a central atom that had 3 points of connection, and we replaced that bond with an unbonded pair, you would have a molecule that looks like this. This is my trigonal, with one bond removed and an unbonded pair replacing it. And that almost looks like a Muppet character, doesn't it? Okay. So in this case, there are 3 points of connection. There are 2 bonds. There's one unbonded pair. This molecule is actually not in your table, is it? I'm sorry? You're not seeing it there? Okay. I didn't think so. This is one of those that didn't make the book, but did make other sources. And this is one I think you will run into. So whether or not Apologia doesn't have any of these in the test or whatnot, but I'd encourage you to know this one as well. It looks very familiar, doesn't it? It looks like a bent molecule, doesn't it? It looks bent. We're going to go ahead and put this down as bent, first of all, but we're going to modify the bent a little bit. Is it the same as the other bent? No. What's it lacking? Another unbonded pair. That other unbonded pair would squeeze them together even more, right? So they're being squeezed together, but not to the same degree as if there were 2 unbonded pairs. If we start with the original shape of trigonal of 120, we know that they're squeezed in a little bit from there, and the resulting angle is 116 degrees. And we differentiate this bent from our 105-degree tetrahedral bent by adding the modifier angular. So this is an angular bent molecule, as opposed to a tetrahedral-based bent, which is simply, we just call it a bent molecule. So 105 degrees for the bent. The angular bent here is 116 degrees. Why? It's squeezed in a little bit from 120. Okay. So we're decreasing complexity here. We got based on a tetrahedral, based on a trigonal. The next points of connection, we're going to have 2. 2 points of connection around the central atom. And you're going to have 2 different cases. for this size. In one case, you're going to have 3 atoms. Points of connection. 2 points of connection means you're going to have 3 atoms, right? Or at least 1 atom in an unbonded pair, which would give 2 atoms, which is the next case. So here I have 2 points of connection. I have 2 bonds. I have no unbonded pairs. The shape or the geometry is known as linear. This is a linear molecule. And the bond angle, 180 degrees. It's a straight line. Now, if I had a central atom with 2 potential connection points, but I removed one of them and put an unbonded pair, do you see at that point I would just simply have a molecule with 2 atoms in it? And even though there is no pivot atom in the geometry, we do have a situation where we have no central atom, but just 2 bonded atoms. And this is the case of the homonuclear diatomics, for example, where we have 2 atoms connected to one another with no pivot. So if it has 1 connection point on either one of them, there's only 1 place they're connecting. There could be unbonded pairs around them, so it kind of doesn't fit in this table real neatly. Matter of fact, I'm going to leave it off the table altogether. We'll just say that this is an exception to the table. So what is this number 2? It's based on linear. Okay, but it's the only one, so if you remember that 2 connection points makes a linear, we have 2 options for the trigonal and 3 options for the tetrahedral. In the last case being 2 molecules that are just bonded to one another like a homonuclear diatomic. Okay? Now, we're going to review real quickly just about polar and nonpolar bonds. And for the bond consideration, we're only going to consider 2 atoms and how they interact with one another when we assess the strength of the bond between them, or the direction of the bond between them. If we were to say that one of these atoms, or these 2 atoms here, are both the same element, in that case it represents a homonuclear diatomic. Let's say that this is a O2 molecule, for example. Which one has a greater electronegativity? They're equal. And so the electrons in this bond pair are equally shared between these 2 atoms. That means at any given point in time, they may be 1 on one, 1 on the other, 2 on one, or 2 on the other at any given moment in time. But as an average, over time, the electrons are equally shared between these 2 atoms. And so as I look at this atom as a whole, it has a net neutral charge. But when I start to look at partial positives and partial negatives over time, it's also neutral. Okay? Because as often as this one is partially positive, it's then also very quickly going to become partially negative, and it balances it out over time. Instantaneously, meaning at one point in time, it may be partially positive or negative, but over time, it's neutral. Everybody comfortable with that idea? Okay. Now, the second option might be that these are 2 different elements. And let's suppose that the element that you see on this side has a greater electronegativity than the element over here on this side. When it comes to the sharing, where will the electron tend to be? It'll tend to be to the side that has the greater electronegativity. This atom is exerting a greater force to obtain an electron. And so that electron, which is still being shared, will tend towards this side. Which means instantaneously, at any given point in time, you could find the electron here, or one at both, or 2 here, or 2 here. It could still be anywhere between these 2. But over time, it would tend to be over here more. And because the electron tends to be on this side of the molecule, this side of the molecule has what we call a partial negative charge. Meaning not at any instant, but over time, this side will have an apparent negative charge to it, and this side will have an apparent positive charge to it. And so we show that with the partial positive and partial negative symbology. So that kind of a bond is called it's called a polar bond. Polar bond is a bond that has the electrons concentrating on one side or the other between the two and giving that bond a direction. Remember how we show that symbology for the polar bond? The part of the atom that's partially negative, let me go ahead and put this on the board. Was that review helpful, the geometries? Okay. Good. And it actually did take me several hours to make all these, so please don't go play football with them, whatever. All right. So as we have two atoms that have a bond between them, I'm not symbolizing oxygens here, I'm just showing, okay, let's make it oxygens. It's a double bond, actually. In three-dimensional, our VSEPR looks like that because each one of them, they have two unbonded pairs, and we're going to show those as being approximately 120 degrees apart. Okay? The electrons here are being shared equally, and so there's no net positive or net negative. I think we used a hydrochloric acid, or HCl molecule, as an example of a polar. We said that chlorine exerts a greater electronegativity. It's a higher force that's trying to get the electron. And so in this case, the chlorine is going to tend to be the partially negative side, and the hydrogen is going to be the partially positive side of the atom. And then we're going to depict that above the bond by drawing an arrow towards the negative and putting a plus sign on the positive side. And so we see this representation. That tells me that it has a single covalent bond with an electronegativity or a polarity that makes this side more negative. Yes, sir?
So you only do the plus and the arrow on one bond, so it's like a double bond?
It one for the whole thing. Yeah, it's going to be, if this were a double bond and it were polar, they would both be polar to the same direction. So you only need the symbol once. So one thing that is a common mistake is that people see this and then assume that it's a double bond and that you've written the symbology on top of one of the bonds. Don't get that confused. This is still a single bond. This is your polarity indicator.
Oh, it's a single bond. Right?
It's a single bond in that top, this part here that I'm going to box right now, that does not represent a bond. That represents the direction of the polarity. So it's still a single bond with an added polarity symbology.
Does that symbol have a name, or is that just a spot that you're drawing?
I don't know if it does. Yeah, we're just indicating,
Like a special symbol?
yes, it's pointing to the negative and indicating the opposite with a positive. Okay, so this is how we assess any individual bond. The next thing was, okay, now we know whether this is a polar or a nonpolar bond. In this case, there is no polarity. Okay, oxygen and oxygen, they have equal electronegativities. There is no partial positive or partial negative because it's evenly shared back and forth. So this is a nonpolar bond. This one is a polar bond, and since it's a polar bond, we then need to figure out, okay, which side is more negative, which has a partial negative, and which side has a partial positive, and we label that with this polarity symbology above the bond. And then we finished with a discussion on, okay, now that we know what a polar or a nonpolar bond looks like, how do we determine what a polar or a nonpolar molecule looks like? And a polar-nonpolar molecule is not the same as a polar or nonpolar bond. Okay? Now we're looking at the molecule, the entire molecule. And the molecule is made up of atoms that are bonded with one another. And so we're going to start assessing whether or not the molecule is polar or nonpolar based upon its bonds. And you stop and think just for a minute. If we have an atom that has bonds and it has nonpolar bonds, it's going to be a nonpolar molecule, right? But if it has polar bonds, Then there's another qualifier we need for it to be nonpolar. Do you remember what that is? If all you have are nonpolar bonds, then you have a nonpolar molecule. If you have polar bonds, you can still have a nonpolar molecule even though you have polar bonds. For those of you who remember that, what you need then, if with polar bonds, is you need perfect symmetry. Let's take a look at this. Nonpolar and polar molecules. A nonpolar molecule is a covalent molecule where all the electrons are evenly distributed throughout the molecule as a whole. Now we're not looking at just one bond. We're not looking at the relationship between one chlorine and a hydrogen. Now we're looking at the relationship between the central atom and all of the other atoms that form the molecule. A polar molecule is also a covalent molecule, but it has an imbalance in the distribution of electrons throughout the molecule. In other words, the molecule has a partial positive side, and the molecule has a partial negative side. It's not simply the bonds have partial positive and negative. The entire molecule has partial positive and negative to it. These definitions are in your book. Okay, so if you're scrambling to write these down, these are in your book. So here, the issue is not primarily the type of covalent bonds, but the overall symmetry of the molecule. If you have all nonpolar bonds, you have a nonpolar molecule. If you have polar bonds, you may or may not have a polar molecule. You would have a polar molecule if you have a lack of symmetry. You would have a polar molecule, or excuse me, you have a nonpolar molecule with polar bonds if you had perfect symmetry. Let's look at a couple of cases, and these are from your book as well. But in this case, CH4, methane, okay? We've got a central carbon, 4 hydrogens attached to it. If we look at the polarity of every one of those bonds, carbon has a higher electronegativity than hydrogen. So as we look from bond to bond to bond, every one of these bonds is a polar covalent bond, oriented with a partial negative towards the carbon and a partial positive towards the hydrogens. You see that? So does this molecule have polar bonds? Yes, it does. But it's a nonpolar molecule. It's a molecule that has polar bonds, but it is a nonpolar molecule because it's perfectly symmetric. The hydrogen in this case are placed in a perfect tetrahedral. This right here, our model of a tetrahedral, could represent this molecule. It has a central carbon, and carbon tends to be the center, so I made it black, because you think, okay? And in this case, the hydrogens are the red. They each have polarity, making them tend to be partial positive, and the center being partial negative in each individual bond, and yet overall, because they're perfectly symmetrically placed, it is going to be a nonpolar molecule. Again, if I'm looking between hydrogen and carbon, yeah, there's a pole here, but there's an equal pole here and an equal pole here and an equal pole here. It's perfectly symmetric. And because it's polar bonded but perfectly symmetric, it's a nonpolar molecule. Which of the shapes are going to have your perfect symmetry? Tetrahedral and trigonal and linear, right? A pure linear, a pure trigonal, and a pure trigonal and a pure tetrahedral have the possibility of being perfectly symmetric. If you have a bent, if you have a planar, if you have an angular bent, it's not symmetric. It can't be symmetric, and you're going to have a polar molecule. The only possibility for having a nonpolar molecule are going to be in your perfect tetrahedral, your perfect trigonal, your perfect linear. And the other thing, too, is for this course, we talked about polar and nonpolar, the bonds, the degree to polarity. Remember I told you before that for this course, if it's not perfectly, if they're not a bond between two identical elements, there is going to be a degree of polarity. Now technically in chemistry, you subtract the electronegativities. And if you get a difference of 0.3 or less, I believe it is, then it is considered a nonpolar bond. There's a range for nonpolar. But what we want you to do here for this course and for this module is say, are they exactly the same? If they're not exactly the same, then there's a polarity to them. Okay. So the CH4 molecule, we're going to say is it has, bless you, it has bond polarity, but it does not have molecular polarity. There is no one side of the molecule that's more negative than the other side of the molecule. If I were to take a hash line to represent a perfect division of the molecule somewhere about and going through the center point, it would always be perfectly symmetrical on all sides. The case over here, we've got NH3. NH3 is our pyramidal. And even though all three of these bonds have the same polarity, we still have this unbonded pair to deal with. And you can see here that I can draw a line through the center atom and it won't have symmetry. And so even though those bonds have a polarity that are all equal in strength, as I look at the total molecule, I don't have a perfectly balanced molecule. And so this molecule would have a net positive side or a net negative side. And so the molecule as a whole would be polar. As a matter of fact, if we look at this, between hydrogens and nitrogens, what is the polarity symbol going to look like? Between nitrogen and hydrogen here. Well, we've got the positive and the negatives, and so you can see from this whole, just from bond to bond, that this is going to be partial positive, right? They already indicated, but I just want to redouble that understanding. These are going to be positive, so this is going to be a net negative, and then on top of the net negative, we have an unbonded pair. So as I look at this entire molecule, not looking at the individual bonds, but looking at the whole molecule, I'm going to see that this side of the molecule is going to tend towards negative, and this side of the molecule is going to tend towards positive. As a whole molecule, it's still zero, because the net charge is still 0. But as we look to it, it's going to have a positive side and a negative side. It's going to have a pole like a magnet. It's going to have a negative pole and a positive pole. And the fact that the molecule has a positive side and a negative side means that it's going to be influenced by other electromagnetic poles that come in its vicinity. If I were to suddenly have this molecule, and let me simplify it, let me just say that my whole molecule as a whole is like a magnet. It's a bar magnet, has a negative side and has a positive side. If I were to bring a negative charge into this area, what would happen? These would repel each other, right? They push away. If I brought a negative to this side, what would happen? They would attract one another. See? The same kind of thing. Because I have a polar molecule, it has a positive side and a negative side, and because of that, it's influenced by other positive and negative forces. We're going to see these during the lab tomorrow. We're going to see these actually play out. Okay? Let's see what we've got next. This is a little bit more complicated, and this is what I was referring to earlier about having perfect symmetry and perfect nonpolarity. Here's a case where we've got the CL4 molecule as nonpolar. It's a perfect tetrahedral, and it has 4 chlorines with a central carbon. So the polarity of every single bond is exactly the same, and it's symmetric. Therefore, it's a nonpolar molecule. Now, on this side over here, we have, again, a perfect tetrahedral shape. But we don't have 4 chlorines. We've got 3 chlorines and a fluorine. Okay? Now, in every one of these situations, the carbon is the net positive side, and the external atom is the net negative side. So the polarity direction on every one of these bonds is exactly the same. However, if we look at the periodic table, let's make an estimate about the relative electronegativity between chlorine and fluorine. Who is exerting more energy to get an electron? The chlorine or a fluorine? Fluorine. It's higher on the periodic table. And the trend is up and right is increasing. So, do you see that in this situation here, the chlorines are all pulling for electrons and the fluorine is pulling for electrons, but this fluorine is pulling for the electron stronger than any one of these chlorines. And because this fluorine is exerting more force, it's going to tend to have an electron more often than its neighboring chlorine would. Be good with that. The fluorine is going to tend to have it more than a chlorine. Now, if it tends to have the electron more than its neighbor, it's going to tend to be negative, right? Relative to these others. Now, these are still going to be partial negatives. And let me draw it this way, partial negative, partial negative, partial negative. But if I were to draw the partial negative on fluorine, and I were to use size to depict it, I would have to put up here a larger partial negative. See that? The fluorine is going to be more negative than its associated chlorines down here. It has a larger electronegativity. It's going to have the electron more often than a chlorine would. So relative to a chlorine, it's going to be even more negative. And because of that, we can now, if we were to draw a dividing line through the central atom, we have one side of the atom which is more negative than the other side, which is still negative. It's just not as negative. And so relatively, it's positive, right? It's still negative net charge, but it's not balanced. And because it's not balanced, we're going to refer to that as a polar molecule. Right? So again, for the purposes of this course, for it to be nonpolar, it either has to have all nonpolar bonds, or it's got to have a perfect symmetrical shape, meaning a perfect tetrahedral, a perfect trigonal, perfect linear. And it has to have the same external atoms in all cases. If it doesn't have those, it's a polar molecule. Let's see if I've got anything else on here. Yeah. Because the key here is between the electronegativity of the chlorine and the fluorine. Fluorine has a higher electronegativity. It's going to be more negative than it would have been had it just been another chlorine atom. Now, what are the consequences of that? The very last part of the module. What are the consequences of the polarity of a molecule, and specifically thinking in terms of forming a solution? When we form a solution, we've got a solute and a solvent. If you take salt and you put it in water and you stir it up, the solute is that thing you put into the thing that breaks it up. So if we think about it just as salt in water or sugar in water, what is the solvent in those cases? Okay. What is the thing that dissolves something else? We have a beaker, and we'll show that it's got a liquid in it. And we're going to pour something into it. We're going to refer to the thing you put into the larger liquid. We're going to call that the solute. And inside, it goes into the solvent. Okay? Now, whether or not these are covalent, polar covalent or nonpolar covalent matters. We've already said that if you put an ionic solution into water, what it does is basically allow those two ions to separate. We have a sodium chloride, we have sodium chlorine put together. It's an ionic molecule. We put it in water. Suddenly there's sodium ions and chlorine atoms, and they're free to move around while they're in solution. And that's how we get electronic conductivity. That's how we light the light, by putting, salt in water and stirring it up. Suddenly it conducts electricity. Why? We've put ions into it, and ions are what we need to transfer electrical charge. Now, if we put a covalent solute in there, whether or not, or the type of bond here, will affect whether or not it dissolves. I'm just going to cut straight to the chase, and then we'll talk about a few examples. if the solvent is nonpolar, it dissolves nonpolar. If the solvent is nonpolar, if we have a nonpolar solvent in here and we put something into it, which is a covalent molecule, if we put in another nonpolar, it dissolves it. Okay? So nonpolars dissolve nonpolars. If we put in a polar solvent, what do you think it dissolves? Polar and ionics. So here's the way to think of it. If my solvent has no polarity, in other words, it doesn't have an imbalance of charges. It's a perfectly balanced. It will dissolve other things which are likewise perfectly balanced. We can get into the whys of that later on. We talk about what does it mean when something actually dissolves. And that is part of one of our discussions coming up. What does it mean when something dissolves? But for right now, just have this understanding. It's kind of one of those things where I'm saying, learn this and know this, believe this, accept this. We'll explain why in another module. But for right now, if you have a nonpolar solvent, it will dissolve a nonpolar solute. If you have a polar solvent, it will dissolve a polar solute and an ionic solute. But if I have a nonpolar solvent and I put in a polar or ionic solute, what happens? It just falls to the bottom of the beaker. It won't go into the solution. But if I have a polar solvent and I put in polars and or ionics, what will happen? It'll dissolve. But if I put in a nonpolar, it'll just stay there. So let's say we're working with water. Is water polar or nonpolar? Okay, let's draw the VSEPR for H2O. Okay, is it a perfect tetrahedral, trigonal, or linear? No, it's polar then. I know that. I don't even have to know what the bond polarities are. It's not symmetrical, therefore it is polar. So water is a polar solvent. So when I think about water, I'm thinking about this case here. So my example would be H2O. If I put salt in water and I stir it up, what happens? Does it dissolve? It does. I've said that that means that it must be either a polar or ionic solute. We know that sodium chloride is a ionic. It's a metal and a nonmetal. There's an electron exchange or electron distribution or an electron giving. The sodium gives up an electron, the chlorine receives the electron, they become opposite charges and they attract. So in this case, the example here would be sodium chloride. Now I'll tell you right now that sugar is not an ionic, but does sugar dissolve in water? Can you take, yes, you can dissolve. So I'm gonna just tell you right now that an example right here of a polar molecule is a sugar. Because I know sugar dissolves in water and sodium chloride dissolves in water. But there are other molecules which are nonpolar, and if we put those nonpolar molecules in water, a lot of them are just going to float on the surface. We'll do that in the lab again tomorrow. I'll see you then.